anyone else wants to join and we have too many technical difficulties, I'm trying to live stream.
There's going to be an echo.
Yeah. So turn down your phone or your Clubhouse, James. Turn down your volume out of your headset, but leave it unmuted. And then Ava, can you tell us if you can still hear us?
So I can't actually turn off the entire Clubhouse volume.
Yeah, just mute it as much as you can. That's fine.
Turns out that I cannot.
Yeah.
Let's see.
So just for everyone joining us on YouTube, we're talking with Dr. James Beacham, who is a member of the Atlas collaboration at the Large Hadron Collider, a past guest on the Into the Impossible podcast, two-time guest on the Into the Impossible podcast. You can see him in our Theories of Everything conversation that we had this past summer with Stefan Alexander and Max Tegmark, mutual friends of ours. And that was over the summer on Theories of Everything. Before that, we had a conversation about theories of everything being explored by experiments of everything. Do we need an enormous solar system-sized particle accelerator to discover new physics? And maybe the answer is no, if the current circular collider, aka CERN, is working well, or LHC is working well enough. So that's what I wanted to discuss today with Dr. James Beacham, who you will know from the movie Chasing Einstein and many other venues. He's a popularizer of science. Last time we spoke, you were maybe working on a book. Is that still true, James?
Still in the pipeline, yes.
Awesome. Well, that would be phenomenal to get from you. So we're live also on Clubhouse, and we've got a bunch of people on YouTube. So welcome, everybody. While you're up here, if you're on YouTube, or you can access James, follow him up on stage, and Ava too. Follow her, and follow her on Twitter, as well as James on Twitter, who is at JB Beacham. Do you have any BitClout coins yet, James? Do you have any BitClout yet? Creator coin?
No, actually, I'm really, really bad at Twitter, and I'm not trying to build any kind of following. So you can follow me, but I'm really bad at the whole game. So
that's true.
maybe I'll be inspired to try to grow a following if there's some kind of cryptocurrency involved. Yeah, maybe.
Yeah. Okay, I'm gonna mute. Sorry, so I'm gonna ask. So James, if you can mute your microphone too on Clubhouse. So mute the Clubhouse microphone. I'm gonna keep mine active.
Yeah.
And now, James, say something to the audience one more time.
So the thing that I need to be able to turn down Clubhouse completely on, so that it's not coming out of the iPad, but it won't let me do that.
Right.
I can't actually turn it off completely.
Yeah, so maybe you can, if you can cover it up with something. It's experimental physics, everyone. Ava, does that sound better now? You can hear James through my Clubhouse, at least? Yeah. Okay, great. Yeah, great. Okay. Good. So we're okay.
Getting some kind of annoying echo or anything like that?
They were, but I think we fixed it. So on YouTube, let me check in with my YouTube friends. Hopefully they are enjoying it as well. So first, I wanted you to kind of give an overview of what is the nature of this big announcement that we woke up to. 99% confidence level detection of potential signature for new physics. First of all, what is this experiment, and what does it mean to discover new physics? Before we get into this particular result that was discussed today, what is the LHCb experiment, and what does new physics mean?
Yeah, so the LHCb experiment is one of the 4 experimental collaborations on the ring of the Large Hadron Collider. So as everybody probably knows, and if you don't, why are you here? The Large Hadron Collider is the largest experiment in human history, and it's a 27-kilometer circular tunnel that's 100 meters underground on the border of France and Switzerland. And in this tunnel, we use superconducting magnets that we have to keep colder than outer space to accelerate protons to almost the speed of light. And then we slam them into each other millions of times a second. And we then collect the debris of these collisions to collect a huge amount of data, and then people like me sift through this data to see if we've found any evidence of new discoveries, new particles that could completely revolutionize our understanding of nature, or if we've seen the expectation from the standard model, or this kind of thing, this, the background expectation, if you will, the noise. And so on that ring, there's 4 different points. Both on the ring, there's 2 beams that go in opposite directions. And at 4 different points on the beam, we cross them and we collide the protons. And at each one of these 4 points, we build a gigantic detector. And by gigantic, I mean really gigantic. So the one that I work on is called Atlas, and it's 6 stories high, and it's 46 meters long. It's like a gigantic soda can tipped on its side and filled with complicated electronics. And so there's another one that's like Atlas that is complementary to it. It's called CMS. So Atlas and CMS were both designed to be more or less general purpose detectors, meaning that they were designed to be sensitive to a very large number of possible signatures of new physics. And that's important because those are the 2 experiments that discovered the Higgs boson in 2012. So, my Atlas and CMS colleagues and I discovered the Higgs boson, hooray. But there are 2 other experiments on that ring that were designed for more specific purposes that can also obviously do completely game-changing physics. They can absolutely make discoveries that completely revolutionize our understanding of nature. And so one of these experiments is called LHCb. And if Atlas and CMS are these 2 gigantic cylinders where protons come in from both sides, a collision happens, and they more or less collect everything that comes out in all directions, with the sort of blind spot being right down the very front part of the beam, we call it along the beam line, then LHCb is designed specifically to look for things that actually go all the way forward. So you have like a proton that comes in, collides, and then the stuff that goes that way, it's a highly finely segmented detector that detects everything going in one direction. So it's very, very far forward. And the reason this was designed this way is because the whole intention of LHCb as an experiment was to be optimally sensitive to these. The intention of LHCb can be found in that last number, B. So the LHCb experiment is designed to be optimally sensitive to particles that contain B quarks, sometimes referred to as bottom quarks. And then in some sectors also, it's occasionally referred to as beauty quarks. That's very specific to like this one particular type of particle physics. A lot of us don't use that phrase. Some people use the beauty thing. I'll be using B or bottom probably in this discussion. And B quarks are really interesting because they have this really fascinating property that when they start to bunch up together with other quarks into mesons or baryons, these particular mesons and baryons can actually have non-negligible lifetimes. So this is a little bit getting into the weeds, but just so you know, LHCb was designed to be optimally sensitive to these particular measurements having to do with B hadrons and other kind of complex mesons and baryons that you can make out of these kinds of quarks. All that's important because it's a perfect example of how the entirety of the LHC program has been designed so that everything fits together in a complementary package so that we're not missing anything. And this result that came out of LHCb today is a perfect example because the LHCb experiment, again, like I said, it's designed to look for these kind of forward-looking particles that kind of go down in one direction. And then, but the reason that's important is that those allow you to make very, very precise measurements of the particular way that these particles decay in certain ratios, in certain directions, in certain preferential places. And so that's basically the crux of everything behind why this result today is so fascinating, because it points out that for us to be able to find new discoveries and to try to push beyond the standard model of particle physics, we need to look every possible place. And so with Atlas and CMS, we look for big particles that might show up, really heavy ones like heavy cousins of the Higgs boson, gigantic Z prime particles, quantum black holes. And so we look for those things, but we also at the same time, we look at very, very precise predictions of this so-called standard model. But that's sort of the background as to what LHCb is.
Yeah, so the paper that was released is in the text box on the YouTube description that I posted. So if folks want to follow along, you can go to Dr. Brian Keating on YouTube. You will find there previously a video of James Beacham from last summer. 2 videos, one a solo episode talking about future circular colliders, and James is perhaps one of the world's foremost proponents, exponents, expositors of why we might need a giant 10 to 20 billion euro or more experiment, and perhaps why that might not be enough. But arguments for that incredible machine known as the FCC are given there. So that's Dr. Brian Keating. That's my YouTube channel. You can see a video of us chatting. We're also live on Clubhouse. I posted the link there, and they talk about the standard model of physics, and they talk about the potential of this strange meson, which is the name of it. It's not an adjective, right? It's not a strange meson.
Yes.
It's a strange meson that emits either potentially an electron or its antimatter particle cousin, or antimatter twin, if you will, called a positron, or a muon, or its antimatter cousin, particle, brother, twin, whatever, antimuon. And there is a violation of this so-called lepton universality. Is that related to the conservation of lepton number? And if not, what is the meaning of lepton universality?
Yeah, so there's a connection, but it's not exactly the same thing. So we need to back up a little bit to really understand the importance of this result today. And it goes back to this thing that we were hinting at earlier, um, uh, where it's, somebody let me know if there's like a weird echo or something like that. I can hear me coming through the Clubhouse thing, but I can't get rid of it. Anyway, so let me know if it's not understandable, and I'll change.
Hold on one second, James. Hold on one second.
Yeah, please.
Ava, can you, what were we going to say? And then I'm going to add in Phil is joining as well. Hold on one second, Phil. Sorry, Ava, can you go ahead? What were we going to say?
Then a bit harder to hear, but mostly the message seems clear, so I don't dare interrupt too much. I also might leave in about 10 minutes, so apologies for that if you need someone else to moderate as well.
Okay. Thank you very much. So we are also joined on video.
What I've done is I've gotten rid of Clubhouse, so it should be okay.
All right. So we are joined by Phil, who is wearing a Milwaukee Brewer sweatshirt. Shout out to Phil and the Brood crew. How are you doing, Phil?
I'm doing pretty well, thank you.
And Phil, are you a member of the team? I'm sorry, I'm not super familiar with you, except for that you come with James's highest recommendations.
No, so I'm not directly a member of the team. So I am on the LHCb collaboration, but I'm not a direct member of the team.
I see. Okay. And can you, for the record, for the court record, can you state your name and affiliation, please?
Sure. So I'm Phil Ilten, currently with both University of Birmingham and also University of Cincinnati, and currently migrating to University of Cincinnati.
Oh, okay. So you will change your sweatshirt to a bear cat, correct? Is that not the mascot of the University of Cincinnati? Are they the Bearcats?
They are the Bearcats. Yes, they are indeed.
So we were talking.
I need to update my hoodies.
James was talking a little bit about conservation laws. I do want to point out, I believe, James, today is Emmy Noether's birthday, maybe, or anniversary of her birth.
Oh, is it really?
Yeah. So
yeah,
can you speak a little bit about that? But you were saying about conservation laws, about lepton number, lepton universality. Can you say more about that?
Yeah. This is a really fascinating thing, and I love this particular field of physics, the sort of subfield that's sort of chasing down conservation laws and things like that at the very, very precise edges, because it speaks to exactly how particle physics and, to my mind, the broader science world really progresses. We sometimes have in our minds this notion, it's like the entirety of the scientific community can be overthrown by, like a straight white male that has a eureka moment and then makes a precise prediction, and then you make an experiment and it finds that thing, and that's the way it goes. Science doesn't really work that way. And so that nowhere is that more apparent than in this thing we refer to as the standard model of particle physics, because this thing came together. It's arguably the most successful intellectual achievement of humankind, because it makes these wonderful, precise predictions as to how the world should behave at the smallest possible levels that basically all come true. It's like completely like mind-blowing how great this thing is. But it came together in a particular way. It wasn't just somebody that sort of by fiat in 1885 said, this should work just fine. This thing, this is exactly what the standard model is, and this is exactly what it predicts. That's not how it came together. It came together sort of by fits and starts. Somebody observed something just they saw in a laboratory, and then some theorist said, this is interesting. I wonder what that means. Maybe it could mean X, Y, Z. And then somebody said, oh, if that's true, then this should potentially show up in an experiment as PQR, blah, 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 blah. And so this is the way it actually came together over the history of the 20th century. And it culminated in this thing that we now refer to as the Standard Model of particle physics. But if you look into the details of the Standard Model, a lot of the stuff that's there that's fascinating and that corresponds to, sort of like makes these predictions and then it corresponds to these measurements that we make, it's just sort of there. It's like there's no real sort of reason for why some of the values of the Standard Model the way they are, and some of the predictions that it makes, and some of the ways that it's organized, some of the things just happen to be the way they are. And so this is why, why it's important to be able to measure everything there is to know about the Standard Model of particle physics, because at the end of the day, just like you were intimating, Emmy Noether, if it's the anniversary of her birth today, this is fantastic because we basically couldn't do what we do at the LHC without Emmy Noether, because she was the one that observed that anytime made a key observation about symmetries in our equations and particles and conservation laws that we would see in reality. And so this leads to this notion that, anytime you have some sort of basically a symmetry, you can think of a symmetry in particle physics as, if I have my equation set up in a certain way, and there's something inside that I can change in a particular way, and it doesn't change with the final answer that I get out of it, that's a symmetry. So for example, I can put like a, for those of you that know math, if I have some kind of standard differential equation, I put some kind of like, some kind of complex exponential in there, and then I do particular stuff to it, maybe do some squares and things like that. That won't affect what the final answer is. So this means that there's some kind of symmetry inside my theory. And Emmy Noether pointed out that anytime you see one of these, there's a continuous symmetry. It means that you have a conservation law. So I don't know how much detail we want to get into that, but essentially what it gets to is the fact that really what we look for in the Standard Model, what we look for in particle physics are deviations from these symmetries or observations of these symmetries. Because like I said, there's a large number of these symmetries you can come up with. You can say, oh, maybe this is a symmetry, maybe this is a symmetry of nature. And this is the part where, to me, it's like it starts to butt into our understanding as sort of like humans with what our intuition is. It's like, oh yeah, of course nature should be symmetrical about some kind of thing. But it turns out it's not. There are certain things in Standard Model that you might think, if you were just sort of, by first principles, I'm going to design an elegant universe, this should be a symmetry of nature. And it just turns out that our universe just chooses not to have this particular symmetry. There's the famous example is CP symmetry, as you know, right? Yeah. And so this is we could talk about that in more detail, but basically, yeah, there's these symmetries that you should, in principle, they could be there. And it's not up to us to choose whether nature observes or violates these symmetries. We just have to go and search for it.
Yeah. So Phil, can you hear me okay?
Yeah, I can hear you. All right.
So this experiment uses muons, and of course the famous phrase by, I think it was Robbie, said upon the discovery of the muon, "Who ordered that?" I think that was Robbie. Was it not? So along James's line, was this something that was serendipitous from the get-go? In other words, was it thought that this would be detectable and that you had to look for it and we didn't have previously enough sensitivity? Or was it truly serendipitous in that it completely was unexpected? You didn't design the LHCb experiment. I know it's not your result particularly, but can you say something about the design of it? Was it intended to go after this effect the way that the LHC without the B was intended to go after the Higgs? Or was it something serendipitous like CP violation, discovered by accident perhaps? Or can you clarify that?
Sure. So I think in the context of this measurement exactly itself, there had been previous measurements of this from other experiments outside of the LHC. So for example, Bell, which was an electron positron collider, where they look at this measurement as well. And they saw something that didn't quite agree with the Standard Model, but the uncertainty on it was quite large, and so not much was thought of it at that point. So when LHCb rolled around and we measured this, we weren't really expecting anything to come out of it, but from the first measurement, we actually saw some sort of deviation, which looked like it could be interesting. And so consequently, there were a whole bunch more measurements that were made, and many of them saw similar kind of deviations. None of them by themselves a discovery at all, but just kind of small niggly deviations or anomalies. And so this started to make it a lot more interesting. So this specific version of the analysis, which was just recently released. This one was very purposely gone into because we had seen all these other deviations. And so that's why this particular measurement was made. But in the larger context of LHCb, it was specifically designed to look at B physics. And one of the kind of beautiful things behind B physics, and for those of you who are listening and know that the B quark is also called the beauty quark, that was indeed a pun. One of the very nice thing about B physics is that you can use it to look for new physics through what we call kind of indirect measurement. So things like CP violation, this is an example of this, but for example, with the decay of the neutron, we knew about the W and the Z boson much earlier before they were directly discovered. And so this is the entire idea behind LHCb and the measurements that are done at LHCb. So to answer your question, no, we were not expecting particularly this, but the type of physics that we look at is oftentimes sensitive to these kind of indirect influences of new physics.
Ah, interesting. So we're hearing some talk, as we often do, about what does it mean to be 99% significant or 3.1 standard deviations. My late great colleague, Professor Hans Parr of the University of California, renowned student of Leon Lederman and others at Columbia, he used to say at 3 sigma, they'll invite you to give a colloquium, but you have to pay for it yourself. At 5 sigma, they'll invite you out and they'll pay for it. And at 7 sigma, you'll get a Nobel Prize invitation to Stockholm. So, Phil, what does it mean, the 3.1 sigma significance? Would you get on a plane if it had a 99% chance of going of staying in the air and a 1% chance of crashing? Or is it better than
No, I would not. The official line from the LHCb collaboration is cautiously optimistic. This is the official line. I would say that this analysis by itself, you might say that okay. This can happen, right? And it does, right? This happened with Atlas and CMS with this kind of diphoton excess at very high masses. Something very similar to this happened where it looked like maybe there was something and then it went away. I think one of the interesting things that's coming out of this is that there are now a number of measurements, so not just this measurement, but other measurements as well, which if you do kind of a global analysis of it, which a number of theorists have done, so for example, there are other ratios you can measure, there are other angular analyses that you can make, that if you take all of these kind of into consideration, you can start seeing some sort of pattern emerge. From the point of making claims about, but you will talk to a number of theorists who certainly will say that a global pattern might be emerging from this.
And James, we were talking a little bit earlier about the need for, or last summer I should say, we were talking about the need for, future experiments. Some people are saying in the comments rather cheekily, send this to Sabina, because she was saying, there's nothing new that's going to be discovered. We don't need a bigger future circular collider. It's a big waste of money. And her normal cheerful, no, I love Sabina. She's actually a dear friend. And she's very extremely important figure, I would say, in the scientific community. But, does this undermine or does this enhance the prospects for a new experiment?
So to me, it can only possibly enhance. But of course, my opinion on the whole thing is that the case for these new machines is already completely rock solid. And anybody that says otherwise is thinking about science in the wrong way. So what this can do, though, is only enhance, because in a good way, right? Because it can help, give a motivation for example, a bunch of new people that are interested in, working on B physics to also join, the effort to start doing some studies as to what we could learn from this type of search in the future. But again, the key point here is kind of what Phil said, and sort of the official line from LHCb, which is in fact always the official line with particle physicists, the experimentalists at least, which is cautious optimism, right? We always have cautious optimism, because the reason why no one is actually calling home to mom yet about 3.1 is because we have seen 3.1 sigma excesses come and then completely disappear with more data. So we know how this works. We have seen this happen before. So this is the notion of cautious optimism. Like Phil said, though, this is really fascinating, cautious optimism, because if you take, because it's not just this as an anomaly that we've seen, or like a, significant anomaly. There have been other anomalies in the so-called flavor sector, which is arguably what this whole kind of thing is, right? Looking for violations in the way that the standard model treats different types of leptons, or in some cases, other types of quarks and things, or, other particles like quarks. In this case, we have seen other of these. And if you kind of like put them all together and squint your eyes just right, you can convince your theorist colleagues that maybe you have like a, collectively some kind of global 5 sigma kind of, suggestion. And none of us are saying this on the experimental side, which is why I think it's important to have experimentalists chime in on this whole thing. We have seen these kind of anomalies come and go. This one, though, is super, super fascinating because, like Phil said, this particular measurement has been done multiple times before. And it's always been a little bit off from what it's supposed to be. At first, it was not so off, like with respect to the uncertainties, you're like, okay, fine, that's, we'll just collect more data. And then it got a little bit better and the uncertainty went down. And now it's at the point where it's actually still off from the expected value, but the uncertainty is really, really low. So that's the whole notion of cautious optimism. We should kind of like set the stage as to why this would even mean anything for a future circular collider. So if you look in just a tiny bit of detail at what's actually going on here, you're looking at some particular thing. So the process that's actually going on here, Phil can talk more about this as an expert, right? But really you have the particular type of particle that's a B plus particle. So this is a meson that has a B quark and is in fact an anti-B quark, and then I think an up quark. And this is kind of sailing along. And at some point, something happens inside where the B quark turns into an S quark. And this is where you said strange. So this is a strange quark. And that's why it's strange, because it's an S, or it's an S because it's strange. And then that's something that made it turn into that could be a few different things. One is that's only possible if you have these like very, very heavy particles that participate in this so-called kind of loop diagram in there that allows this to happen. And then what happens in that kind of loop is as that happens, you get, for example, W bosons and maybe a Z boson, and then it spits off 2 leptons. And this is what you were saying, Brian. It could end up being either electrons or, electron-positron pair, or a muon-anti-muon pair. And so that's possible for that to happen just given the standard model. But it's extremely rare, and you can also calculate that really, really precisely. We know quite a bit about that. The problem is that we see this not, so then the thing you might then, so the test here is actually this notion of universality, right? Where it's like you might think that this thing that comes out, the leptons, there's no reason to think that there should preferentially decay to electron-positron versus muon-anti-muon, or for, to be complete, tau or anti-tau, which is another heavy cousin of these electron and muon. But in this case, what we're seeing is that, yes, a little bit preferentially, this decay tends to be accompanied by and not so much muon anti-muon. And I think I'm frozen here. Please let me know if you can hear me.
I hear you.
Okay, so yeah, so that you start to think, what is making this happen? Is there something else in this little blob, this sort of unknown blob, that is not just these heavy particles like W's and Z's, the ones we know and love, or because just given those standard model particles in there, you should get electron, positron, and muon, anti-muon at the same rate. There's no reason to think otherwise. We've never seen any violation of this anywhere else. In this case, there is some kind of preferential decay. And one way to explain that is if there's some new particle, some completely wild exotic thing that could be in there that is somehow making it so that, for example, it's too sticky inside for muons, and it lets off electrons and positrons at a higher rate. And this could be so this is the place where the potential discovery is, right? That's the money thing. That's the money blob right there. It could be, for example, a new force carrying particle like a Z prime, which would be totally revolutionary because there's no other forces in the standard model. It could be something called a leptoquark. This is a bizarro particle that both couples to leptons and quarks. It's totally weird. So the mass scale of this particle could in fact be something extremely high because it's sort of like in this loop here. And Phil can probably talk more about this, but because it's in this loop, it in fact can have a very, very high mass, this particle, and because we can't actually discover it directly in that particular process. And for example, this intermediate particle, this completely wild new thing, could potentially be, I don't know, a leptoquark with like 10 TeV. We can't make a 10 TeV leptoquark directly at the LHC, which means we would need another machine. We don't need further justification for a bigger machine, but this would be extra justification.
Very cool. So Phil has muted himself, but I do want to ask him to unmute because I want to ask you, Phil, when you do these types of experiments, when one does these types of experiments, what is the extent that physicists such as ourselves will rely on symmetry? In other words, we'll do a test that is designed to be a null result, actually, in order to test our understanding of the particular peccadillos of the experiment itself. In other words, what sorts of tests do you subject data to? Maybe, again, not speaking, you're not a member of this team that was announcing today, you work on the same instrument, you're familiar with the techniques. What sorts of techniques do you use to go to assurance to prove, as Feynman says, that you haven't been fooled, because we all know that we are the easiest people to fool. So can you talk a little bit about the types of null tests, jackknife tests, etc., and then we'll come back.
Sure, absolutely. So one of the kind of really nice things about this result is that it's a ratio of basically two different processes, as James said. One is where you have a B plus meson and it's decaying into a K plus meson, and then mu plus mu minus, so a muon and an anti-muon. And then you do the exact same thing, except it's decaying into an electron and a positron. And by taking the ratio of these two results from a point of view of theory, a lot of uncertainties that are introduced cancel out. So this is, from a theoretical point of view, a very nice measurement to make. From an experimental point of view, electrons and muons act very, very differently in our detector. And so this means you really have to take that into account. So from the experimental point of view, we actually don't do a single ratio like this. What we do is actually a double ratio. And we utilize and rely upon actually lepton universality in a different process where we know that it does hold and where we know that any type of kind of new physics would be entering at a rate that wouldn't really matter in the measurement. So in this particular measurement, we use what's called the J-psi. So it's a bound charm anti-charm state. And this decays into muons and electrons. And we actually use this type of decay to validate the measurement itself as well.
Wow. Now,
hopefully that answers your question.
Yeah, it definitely did. James, we hear them talking about new physics and maybe even a fifth force. I wasn't aware that this would necessarily imply the existence of a fifth force, but maybe rather a new decay channel, additional, in the same way that the observations made by C.S. Wu, Chensing Wu, back in 1957, they didn't reveal a new force of nature. They revealed that the weak force had certain parity violating properties. So to what extent is that actually accurate, that this would be a new force of nature rather than just a new property of existing particles found in nature?
So the would be that if you do, this result is actually a consequence of a new particle that would be a new force carrying particle. That's the kind of simplest answer, because the only, the standard model describes three of the known forces of nature like so wonderfully well, just like it does such a fantastic job with three of the known forces of nature. It says nothing about gravity, which we know that it's incomplete. But each one of these forces of nature has so-called force carrying particles associated with it. And so for the electromagnetic force, it's the photon, and you're all bathed in photons right now. So that's the force carrying particle of E&M. For the weak force, there are these three gauge bosons or force carrying particles, the W plus, W minus, and the Z. And then for the strong force, there's a bunch of gluons, and they're all basically similar properties. But that W and the Z are really interesting because the weak force has this really unique property where it has these three different gauge bosons, and these are so-called force carrying particles. And in fact, this whole notion of lepton flavor universality is very deeply connected to things like gauge bosons. It's really fascinating because there's certain symmetries in the standard model, these so-called symmetries that that we can measure, that are there because of the particular gauge structure of the standard model, the particular mathematical structure. And there's other ones like this lepton universality that is sort of accidental. In fact, we just call them accidental symmetries. They just happen to be preserved up until the moment that somebody sees a deviation from that, then they'll be violated, right? And so the Z is really important for that. So the Z boson back at LEP, one of the most fascinating things that LEP did, which was the experiment in the tunnel before the LHC was there, was the fact that they measured the Z boson branching ratios of the leptons down to extreme precision, and they're basically all the same. So this indicates that Z as a particle is really motivating for basically new things in the future, because if there is a new force of nature, it would make sense that it could have a gauge boson similar to a Z. So we refer to this as a Z prime, or sometimes a dark photon, or things like that. And that's actually a very fascinating side project, because it's something that Phil and I both work on in separate ways, looking for the so-called dark photons in particular ways. But if you were to have, so one of the ways you could explain this violation is if that, again, that thing in the blob there that makes this, this B turn into an S plus a couple of electrons preferentially over a couple of muons, something else in that blob could in fact be a Z prime particle. And if the Z prime particle exists, then it could be a new force carrier. So that, again, that's something that we can't necessarily directly discover at the LHC, because number one, we haven't seen any evidence for direct production at, say, Atlas and CMS for these Z primes. But instead, what we do is we could see conclusively at LHCb and potentially at Atlas and CMS. I know for a fact that Atlas and CMS have similar results and complementary results to this LHCb one in the pipeline right now. Let's cross our fingers that they will be out, sometime later this year. We don't really know. Timelines are different. But if we were to see, so we haven't seen any Z primes at Atlas or CMS or LHCb just sort of directly produced and then decay into something, which is really what Atlas and CMS are good at, right? If the LHC smacks together two protons, a big fat particle sits there for a second and then decays to something immediately, we'll find it. We haven't seen any of these so far. So instead, we have this sort of hint, this indirect hint. And we can then say conclusively, if this turned into, say, a 5 or a 7 sigma thing, we can say conclusively this is a new effect. One of the explanations could be a force-carrying particle. We won't be able to say definitively with just this particular measurement, but this is a perfect example of how all these experiments are complementary, right? LHCb can, for example, see something that's like a big sort of hint and like a conclusive sort of evidence of something new. And everybody goes, okay, drop everything, look directly at this, build a gigantic, 100-kilometer tunnel, a new detector, a new accelerator, a bunch of detectors, and make sure this is exactly what you're looking for in addition to everything else. Mm-hmm. So I really like the way it all fits together.
And Phil, we're getting questions in the audience about, on YouTube at least, we'll take questions from Clubhouse as well, but I remind you to go to Dr. Brian Keating on YouTube if you want to see some of the links we're discussing and see these physicists' faces. It's nice to connect a person to a voice. We got about 15 minutes before it gets super late over there in Europe, and we have to go to take care of other less existential items like picking up kids. But maybe I'll stay on Clubhouse for a little bit, just the same. So, Phil, some are asking about implications for dark matter, dark energy, new forces. James mentioned a little bit about dark photons, or I forget the other term you used, James. But Phil, can you talk a little bit about implications in cosmology, from the very small to the very biggest?
Sorry, Brian, could you repeat that last bit there? That kind of broke up for me there.
Oh, just wondering if you can comment on the implications for cosmology, potentially, if this result is confirmed.
Yeah, so first of all, the current, so I wanted to touch very quickly on what James said about some Atlas results and CMS results, also kind of being consistent with this anomaly. So they have upcoming results, but they also have previous results, which when you put them, as I said, into kind of a global picture of everything, you can start to maybe get an idea of what kind of force this would be if it truly is a new force. And so James mentioned a Z prime or something like a dark photon. This is certainly a possibility. There are some other ones out there that in the current kind of fits of all of these anomalies together are preferred. So for example, James mentioned already the leptoquark. This is a pretty crazy force which kind of is able to interact with both leptons and quarks at the same time. And this is actually a very nicely preferred model. Another type of model that's preferred is a particle that would be similar to the Higgs boson in the fact that it's what we call a scalar particle. But it's different in the fact that it would carry color from the from quantum chromodynamics, and so this would really be some sort of exotic particle. Now the question is, how are these possibly, could these be connected with dark matter in the dark sector? The answer is yes, but the problem is that we won't necessarily know how they're connected from just terrestrial-based experiments. So you could make some guesses about how it would be connected, and you can certainly make a lot of speculation about how it would be connected. But to really be able to kind of make conclusive statements about that, what you would really want to be able to do is see how dark matter directly interacts with the matter that we have here on Earth. So it gives you plenty of chance to speculate, but you wouldn't necessarily be able to say anything conclusive about it, that's for sure.
Got it. Okay, I'm going to open now up to Clubhouse for the next question. There were some hands raised.
Brian, I want to.
Yeah, go for it, James.
Brian, I want to show something really quickly, just to.
Yep.
Yeah, exactly. Get up a nice question. I'll just mention here, jumping on what Phil said. So this notion of chasing down anomalies and chasing down, deviations from expectation is, it has a very long history, not just in physics, but even in the sort of like LEP and LHC days, right? And so this is, Phil pointed out a good example of the other complementary measurements from ATLAS and CMS. I should probably just mention explicitly, for example, last year, ATLAS, my experiment, released a result that was really fascinating, looking for a similar type of lepton flavor universality, kind of a violation of this universality, with a very kind of novel way, looking for top quarks as they decay to W quarks, and then particular types of leptons. It's a little bit, the details, you can get into the weeds if you want, but really what it is, it's a fantastic thing, because this is in fact, we did not see a violation from this universality, which was in fact contrary to what had just a hint of something that had seen way back in the LEP days. So it's again, particle physics is a marathon. It's not a sprint. You have to be very patient with these things. So this is, for example, I think it was a 2.7 sigma excess or deviation from back in the LEP days that just last year was finally ruled out and said, no, in fact, it's consistent. So this is the notion of cautious optimism, right? It's like, yes, we're all, raising our eyebrows, like on a scale of 1 to 10, if 10 is like a discovery, this eyebrow raise is about like a, maybe like a 4 or something like that. We're keeping an eye on.
Okay, great. So we have a hand up. We have Radoslav is in Clubhouse. So raise your hand if you'd like to speak with Phil or with James Beacham or myself. Radoslav, go for it.
Thank you, Brian. Thanks for hosting and letting me join. And James and Phil, and thank you very much for taking the time to go through the result. I'll be quick. A few questions here. Looking at the plot on page 8, figure 8. It looks like Babar measured this and agreed directionally with what you're seeing at LHCb, but Bell, granted, error bars were massive, was on the other side. Babar, as I recall, was slack, right? And that was running about 20 years ago. And then the other couple of questions, as I recall, Babar was an attempt to try and understand why there's more matter in the universe as opposed to antimatter, given that we think some hints might be contained in these B mesons. So is there any potential explanation that could revolve around why there's a preponderance of matter as opposed to antimatter? And lastly, I gather that kaon also decays into neutrinos, and I'm wondering, could there also be perhaps a connection to neutrino oscillations that we don't quite understand yet that may be giving rise to the asymmetry?
Great, thank you. James or Phil, do you want to take that? Either one of you guys can take a crack at it.
Sounds like a great Phil question. Go ahead,
Phil, go for it.
Sure. Yeah, sure. So you're right. So if you take a look at this figure, there are results from Babar and then also from Bell. Both of these experiments are B physics experiments. So in other words, they're specifically focused on looking at B mesons. And as you mentioned, one of the things that they're looking at is the CP violation in B decays, and how this connects to the idea of this matter-antimatter asymmetry, and whether in these types of decays you can have enough violation like this to basically account for the matter-antimatter asymmetry in the universe. And so this is certainly one of the big picture questions that's a driving force for all of these experiments, like Babar, Bell, and LHCb as well. So in that context, Babar, Bell, and LHCb, from a kind of physics viewpoint, all are focusing on very similar things. They're very different, of course, in the setup, in the fact that LHCb is on a collider where we collide protons, And typically for B physics experiments, this can be a little bit hard to do because it's a much noisier environment. And so in this context, LHCb is different. This is a disadvantage, but there are also a lot of advantages that you have as well in terms of the amount of data that you can collect and the type of data you can collect as well. So in context of the Babar and the Bell results, they didn't have quite as much data available to them. And you'll see that within the data that they have, Babar and Bell are consistent, whereas the LHCb results are not. You can also look at some other results from Bell and Babar that are related to these measurements. You can look at them in these different bins of what's called Q squared. So this is basically the mass squared of the two leptons. So the mu plus mu minus or the E plus E minus. And you can look at them in these bins. And in this case, actually, you will see that some of the results from previous experiments also see this discrepancy, but typically they will have significantly larger uncertainty. This has to do with the number of events that they've seen and also how well they can peg down the uncertainties of their experiment. So I think that answered some of them. I think there was one more that slipped my mind that you had asked.
Neutrino oscillations and the count decay, right? Isn't the B plus decays into a count, and that ultimately goes into a lepton and neutrino?
So what we see here in terms of the lifetime of these particles in our detector, we see, in this case, the K plus. We don't see the decay of the K plus. So we will just see the K plus itself and not its decay. So in this particular experimental setup, the decay of the K plus is not particularly relevant. And the reason for this is because
it's much cleaner measurement. That's great. I didn't realize that.
Yes. So actually, that's why.
It's just a testament to how wonderfully these detectors are designed, that you can actually do something like that, right?
Right. Very good. Thanks, Roslav. Are there any other questions in Clubhouse? We can take that. Otherwise, we have some more questions on YouTube. And I want to remind folks to please look into following James Beacham on different social channels. He's not super active by his own admission, but I find him to be quite entertaining to follow in all things. But he's very shy, so you have to get him out of his shell. But please subscribe to the. You can find him on Chasing Einstein, which is a wonderful documentary. You can find that on iTunes and on YouTube, and it features my very good friend Alina April, who is the Margaret Burbage Visiting Professor of Physics just a year ago. I can't believe how much has happened in that year. She's also featured on my channel, so please do subscribe, give a thumbs up, leave a comment here, and this will be on iTunes and all the other places to get a podcast later on. Phil Ilten, where can people find you?
Please do follow me. Sorry, please do follow me on Twitter, because that's the only place that I give like a broadcast tower for what I do, even though I'm not so active. That's my broadcast tower. Go, Phil.
Yep. I do not have any social media accounts, but you can email me if you would like.
That explains your phenomenal productivity compared to me, at least. So these decays are really interesting, and I maybe I'll say controversially that it seems like maybe it'll be even more shocking than the Higgs discoveries that you and your teammates made, in that if you discover a new force, well, that's a lot better than kind of an old force that we knew and loved and kind of had our hunches about. This, I should point out, from the data that was published, it seems like the significance went up significantly, to be redundant, from when there was, 5 inverse, femtobarn? You guys characterized this in a weird way. Luminosity basically almost doubled, and yet the error bar shrank or improved by something more than a factor of than you'd naively expect. So I think that's quite interesting. Anyway, we have a comment from Matthew. Is that Matthew Fox on Clubhouse? Go for it. Are you there? Let's see. I have to invite him up. I invited him up, but he is not coming up. So let's see.
My apologies. This is my first time coming up here.
No problem. Matthew, go for it.
Have we discovered part of a new dimension?
I don't know that we characterize it as a new dimension, a new force. James, why don't you take that?
Potentially could be a new force, but I wouldn't go so far as to say that this particular measurement, or this, again, let's make sure this is not a discovery. This is not even an observation. This is what we call evidence. So This is the cautious optimism. The message you should take away from this discovery is that LHCb has not discovered a new particle yet. This is a hint for something. But I wouldn't say that it has anything to do so far with extra dimensions. There are some potential sort of like very, kind of speculative theories that would involve, grand unified theories and beyond that, like extra stuff where you can, if you squint just right and you talk to the right theorist, you can kind of explain some of the things that we don't understand about nature with, for example, new dimensions of space. This is not exactly what is happening here. But again, any new discovery could point the direction to where any new discovery, like for example, a discovery of a violation like this, could in principle point the way as to where we could then find a discovery that would relate to things like extra dimensions. So one of the big things about the Standard Model, that's one of the biggest mysteries, is that it has nothing to do with gravity. And we know that gravity exists, so we know for example it's incomplete. And one of the ways that, for example, gravity could be somehow go with the Standard Model is if, for example, there were other dimensions of space. That's, we don't, but how that actually happens, we currently have no clue experimentally. There's no way for us to connect those things. What we need first is any kind of hint, any kind of conclusive 5 to 7 sigma hint that the Standard Model has some new thing that we have discovered. Once we find that hint, once we find that portal, the whole game changes, and that's when we might be able to find evidence of really wild things like new dimensions.
Very cool. So a couple more questions from Clubhouse. I'll invite you guys up. Alexei and Othman, is that right? Am I pronouncing that right? Othman? Alexei, go for it. You're on with James and
Hi.
Phil.
Sorry, I was just passing by and noticed this is a very interesting talk and a very interesting discovery. My question is maybe a little bit more on the technical side. Does the significance of your results depend on how you bin your Q-square distributions?
Yeah, Phil, do you want to take that? And just to reiterate, this is not my guest today, Phil Ilten and James Beacham are not directly affiliated with this result, although they're both particle physicists working at the cutting edge at LHC at CERN. Phil, take that, the dependence and binning with respect to Q squared.
Yes, it does.
Lest you thought my audience was mathematically shy, guys. I mean, come on, do I have the best audience in the world? I mean, you're getting questions about Q squared binning dependence from a new number two. Thank you, Alexei. Yes, go for it, Phil.
So yes, it does depend upon that. And so the bins are carefully chosen by us when we set up the measurement to ensure that we minimize theoretical uncertainty and also experimental uncertainty as well. Mm-hmm. So this is a very specific way that it's done. Also, in terms of the binning of Q squared, at lower values of Q squared, you are sensitive to what's called the C'9 Wilson coefficient. This is very technical jargon, but what it means is you're sensitive to a specific cells within the model. Whereas at higher Q squared, you have more sensitivity to C'10. Uh-huh. So these are chosen very specifically.
Excellent. Let's see. Time for one more question, and I have to wrap up the stream, and I know the guys have to go too. It's late, at least in Europe. Phil, are you in Europe right now?
No, I'm in Cincinnati right now.
You're in Cincinnati. Okay, so you're just in.
Yeah. So this brewer's jersey. This brewer thing is even more controversial.
All right. All right. So, Othman, you are our final questioner. Can you make it quick?
Yeah, absolutely. So, given what will it take basically to confirm this result? I know that LHCb, like the point in resolution of the detector, is designed in such a way to pick up these decays. Will Atlas and CMS be able to match that, at least the precision? And if not, what will match it besides LHCb essentially collecting more data and then getting a better resolution for the measurement that they have done now?
So as an Atlas man, I can take the first stab at this one. So Atlas and CMS will not be able to do the exact same analysis because of the design of the detector is slightly different, but we can do a sort of complementary method. And I don't actually know the answer because it's still being analyzed right now. I can't tell you, what Atlas is planning to release with respect to this measurement, but it likely will be complementary. Let's put it that way. I don't think I would suspect that with just run 2 data, we wouldn't be able to make a similar sort of statement. Again, I could be totally wrong, and so this is the sort of ambiguity before the results become, before they're fully vetted inside the collaboration and then they become public. But I have a suspicion that it's going to take at least some run 3 data for us to say conclusively whether this is going to be, if this is going to turn into something, if not the high luminosity era. And maybe Phil knows more from the LHCb side, whether you're going to need high luminosity LHC data to really take this to the potentially the 5 sigma level, or rule out, or if it's just going to be run 3.
So first of all, I think before you were to get really excited about this, you would absolutely want another experiment other than LHCb to confirm this, right? This is why we have multiple experiments on the LHC. And so absolutely, in terms of CMS and Atlas, so for example, they can reconstruct electrons differently. They can do a slightly better job in reconstructing electrons in certain scenarios. And so you would really like to see something come from CMS and Atlas in this respect. As you said in the question, the resolution for kind of the lifetime, so being able to see the B meson in the first place is not quite so good. CMS and Atlas weren't designed specifically for that, but they will be able to see this at some point. One of the very exciting things about LHCb in terms of the significance of this result is that in the upcoming data taking, we're completely changing the way that LHCb is able to take data. And so we're going to be able to take a whole bunch more data. So while we're going to be taking roughly double the amount of data that we currently have, or more than double the amount of data that we currently have, it'll be even better than that because of the way that we're able to collect even more data. So this is also something very exciting. Right. The other thing I want to say here, though, very quickly, is the LHC isn't the only game in town. Bell 2 is also online now as well. Right. And they have a very, very clean environment. And so the hope would be that they would either be able to confirm or deny this anomaly as well.
Awesome. Guys, thank you so much. I can't thank you guys enough. James Beacham, Phil Ilten, soon to be at the University of Cincinnati, a phenomenal institution. James Beacham and I will have many conversations that are stored on my YouTube channel, Dr. Brian Keating. Please go there, subscribe to the channel, use your finger. Don't get carpal tunnel syndrome in these radical times. Please press the like, subscribe button so you avoid that particular malady. Gentlemen, thank you so much for sharing your time on this exciting day. Please agree to come back when you have new results or anytime you want to come on. We have the smartest audience in the multiverse. For now, signing off on behalf of my friends all around the world. Here's to more great scientific discoveries. Good night, everybody. Bye-bye.